Notice you have seen this before and that. In the last video, Physics 09, we covered these three formulae. So far, we did 15 of these formulae, the ones in the white font. Now we will consider formulae 10 and 11, these two. They are used to calculate the resultant of two forces. To be clear, CSEC does not really require you to know how to use these two formulae for physics. And while you do not have to memorize them for CSEC math, because you are given a formula sheet with these two formulae in it, you will have to know how to use them. So why do we take the time to learn them in physics? Well, you can easily check your answer using these quick calculations when CXC does require you to find the resultant of two forces by scale drawing. And secondly, if you also take CXC mathematics, this serves as a reinforcement so that you learn to solve questions that require the use of these formulae faster and better. Now, these two formulae generally go together in calculating resultants of two vectors that are not at right angles to each other. The first one to calculate the magnitude and the second one to find the direction. Now, if these two forces are at right angles, then we can use Pythagoras' theorem and one of the trigonometric ratios to find the resultant and its direction. But we will deal with that in the next video. So let's look at example 1. Two forces, 500.0 newtons and 800.0 newtons, act at a point at an angle of 70.0 degrees to each other. Notice this one has 4 significant figures, this has 4, and this one has 3. So we will have to limit our answer to 3 significant figures. By calculation, find their resultant and the angle between the resultant and the larger force. In order to do that, we need to know something about the parallelogram law of two forces, which simply states that if two forces acting at a point are represented by the adjacent sides of a parallelogram, then the diagonal from that point represents the resultant in both magnitude and direction. So first, we will make a sketch of the forces. Now, this is a sketch. It is not drawn to scale. We would normally put the larger force on the horizontal axis and then estimate the angle and draw the other force. It's a sketch. Secondly, we will complete the parallelogram by drawing in that side which is parallel and equal to this, and then this side over on the right here, which is also parallel and equal to this side. So this is a sketch. Third, we will draw the diagonal from the origin, label it lowercase a, and the angle opposite that as uppercase A. So this is our diagonal here from the origin, that diagonal going that way. We label it lowercase a, and the angle opposite it, we label it uppercase A. We also write in the value of this angle A, which is always equal to 180 minus the angle between the forces. In this case, it will be 180 minus 70, so we get 110 degrees. This angle here, A, is 110 degrees. The uppercase letters are angles and the lowercase letters are sides. If an angle is uppercase, the side opposite it is the same letter but lowercase. Example, an uppercase C for this angle here and a lowercase c for that side over there. Next, we will write the sine rule, which is a squared is equal to b squared plus c squared minus 2bc cosine A. We remove the square from here and make it square root. And now we have to be careful with the brackets, but I will talk about that more in detail later on. So if I want to do this all in one step, I will start with the square root, 3 open brackets, then 800.0 close bracket square plus open bracket 500 close bracket squared, and we close a bracket there, minus an open bracket here, 2 times 800.0 times 500.0 times the cosine of, and you have another bracket here, and we close it with 3 brackets. Now if you enter that in most calculators, press equal, you will get this answer, and I will actually demonstrate that later on in this same video. Now this is the magnitude, but since we are using 3 significant figures, we will round off at this point and we get 1080 newtons. Correct to 3 significant figures. The magnitude of the resultant is 1080 plus or minus 5 newton, because remember we are rounding off at the tens position. That's the magnitude. But we also need to find this angle here. So now we want to find angle C. We will now use the sine rule, which says that A, which is side A, over sine A. Now remember, that is side, that is angle. A over sine A is equal to B over sine B, which is equal to C over sine C. These are all ratios. So when you divide side A by the sine of angle A, and you get an answer, you will get that same answer if you were to divide side B by the sine of angle B, which is the same answer you will get if you were to divide side C by sine of angle C. Now, since we are not using B in this example, we will cross that out. A over sine A is equal to C over sine C. If you cross multiply, this sine C goes over that side, so you get A sine C is equal to C sine A. You remove the A from this side, and it becomes divided on this side. And then you remove the sine from this side, and it becomes inverse sine. So C is equal to inverse sine of C sine A over A. Let's put in the numbers and see what we get. This is side sine of 110 degrees over A that we calculated, but we would not use the rounded up value. We will use this value. If you were to put all of that in your calculator, you will get this. So C is approximately 25.8 degrees. And so our answer is 1080 Newton at 25.8 degrees from the larger force between the two original forces. Now we are going to do that same question, and this time we are going to do it by scale drawing. We still need a sketch. So we make a sketch like we had originally, but previously that is all we did, and then we went on with calculation. Now that we have the sketch, we are going to draw that sketch very, very accurately. We choose a scale. Let 1 centimeter equal 100 newtons. And so 800 newtons will be 8 centimeters, and 500 newtons will be 5 centimeters. And these measurements are reasonable to get on a page. And this is our scale drawing. So first of all, we draw a line here. We label it 8 centimeters, 800.0 Newton. We measure that angle up there, and through it, we draw a line 5 centimeters. We write in the 70 degrees here, and we have expressed the information we are given. Then we complete the parallelogram by locating this point, drawing in that line up there and this line here. And then we draw a diagonal from the point of origin So now that we have the drawing, we measure the diagonal from here to there. We measure it and we get 10.8 centimeters. 10.8 centimeters, that's 11. We multiply it by our scale because we said our scale is 100 newtons per centimeter. And so we get 1080 newtons, which is exactly what we got when we did the calculation. So the resultant is 1080 newtons. And then all you need to do is to find the angle. We take a protractor, set it up here, and we measure the angle from here to there. Let's see that a little closer. Measure the angle from here to there. We are at 0, 10, 20, 25, 26. So we are somewhere at 26. And so we get 1080 newtons at 26 degrees. Which is not bad really. Yes, when CSEC requires you to solve such a problem by scale drawing, you can quickly check your answers by using the sine and the cosine rules to find out how close you really are. Let's try one more like this. We'll go a little slower this time. Two forces, 87,000 newtons and 65,000 newtons, act at a point at an angle of 100 degrees to each other. Find the magnitude of their resultant and the angle between the resultant and the larger force. Well, we will solve it first by calculation, and then we will do the scale drawing. First thing we need to do is make a sketch. Normally, we draw the larger force as a horizontal force. We write it in there. This is a sketch. We estimate 100 degrees, and we draw the other force here, which is 65,000 newtons. We then complete the parallelogram, still a sketch. Complete the parallelogram by drawing in that side and this side. We don't have to do it accurately, it's just a sketch. Next, we draw from the point of origin, the original point here. We draw this diagonal, write in lowercase a. Opposite that lowercase a, which is the side, we write in the uppercase a, which is the angle, and we also write in how much the angle is. And in this case, it would be 180 minus 100, this 100, because these two angles are supplementary. They are co-interior angles, two parallel lines, and you have a transversal, which is this. They are co-interior angles. So if we know this is 100, we know that this is the remainder from 180. So we then write in C over here and make sure that this is 65,000. After all, it is opposite to this side here, opposite and equal to it. Label this part, this side here, B. So now we have A, side A, angle A, side B, and side C. And that's all we need to calculate A. Now remember, this is still a sketch. You write the cosine rule and change its subject from A squared to A. So this is our cosine rule. Remove that square from there. And so we get A is equal to the square root of everything else on the right-hand side. Now, if you plan to do all of this in one step, we need to put in some brackets so that we will not end up with a logic error from the calculator. And to do that, use a curly bracket here to begin and a curly bracket here to end, so that you will find a square root of everything else in between there. Use a parenthesis here to work that piece out, use a square bracket here, and you close that square bracket over here, 2 times b times c times the cosine of a. Some calculator, you don't need to use this bracket. And so you would be able to do all of that in one step. As I said, you need to know what your calculator can do and how it can do it. So we have that. We now substitute the values that we know. B is 87,000, we square it. C is 65,000, which is squared, minus, open bracket, 2 times B times C times the cosine of A, which is 80. And you could do all of that in one step if you are careful with the brackets. You simplify this right-hand side here, and you get 99,146.6 newtons. And if we round that off to two significant figures, because that's all we have, two significant figures, okay, that's all that we have, and we get 99,000 newtons, and you can easily make that to 99 kilonewtons, since kilo means 1,000. And that should suffice for CSEC exam. This should suffice for CSEC exam. However, if you are not sure and you want to make sure that CSEC understands that you did round off at this position, you could always put in plus or minus 0.5 kilonewtons. So we got this resultant over here. We got that. We now need to find this angle here. Clearly identify the angle. Now we write down the sine rule, which is A over sine A is equal to B over sine B, which is equal to C over sine C. We want this angle. So angle C and side C will come into play. We will have to use angle A and side A. So really, for this part, we don't need this B nor that angle B. We don't need that. So we will cross that out. Cross it out. And we are left with A over sine A is equal to C over sine C. We cross multiply. We move the A from here by dividing both sides by A. So A comes over here. Then we remove the sine from here by multiplying both sides by inverse sine. So now that we have this, we can substitute the values we have. We will use A as 99,146.6 newtons. And so we know what C is. C is 65,000. We know what A is, still 80 degrees. And we know what that is, angle A is 80 degrees. And we know what side A is, which we just calculated up here, which is this. You can do that one step as is. And when you do that, you will get 40.21 degrees. We round it off to 40 degrees. Now, overview of finding the required angle, which is this. This is what we did. A over sine A is equal to B over sine B is equal to C over sine C. You work through that, and you remove the B from there because we don't need it. You change the subject to make C the subject of the formula. You substitute your values here, put that in your calculator, and you come up with 40 degrees. So our answer is 99 plus or minus 0.5. Now, that was what we calculated for the magnitude. And now we have the angle as 40 degrees plus or minus 5, because we are rounding off at the tens position, one significant figure, and we take half of that position plus or minus. So if you want to look at the whole page, this is what it looks like. This here has to do with calculating the magnitude, and this here has to do with calculating the angle. Now, it is not as complicated as it looks here if you do that about 4 or 5 times. After a while, it becomes very, very easy. Okay, now let's do the same thing by scale drawing. We still need a sketch, so we had the sketch from before. If we didn't have it, we will do it now. Remember, this is a sketch. Now that we have the sketch, we will choose a scale that would fit on our page, such that our drawing will be between 5 to 15 centimeters. In this case, we would say 1 centimeter is 10,000 newtons. Therefore, 87,000 newtons will be 8.7 centimeters, and 65,000 newtons will be 6.5 centimeters. We construct a line to represent the larger force, and we write it in 8.7 centimeters, which represents 87,000 newtons. After that, we take our protractor and we measure an angle of 100 degrees. Now, don't get confused with this 100 here. We are starting from this 0, so we count all the way around until we reach that 100. Once we reach that 100, we draw a line from the origin here through the point we marked off, 6.5 centimeters, writing 65,000 newtons, and then you write in the 100 degrees here, and this, at this point, we have drawn to scale the information we were given. We need to complete the parallelogram, so we locate this point here, and we draw a line from over here to there to get that side of the parallelogram, and a line from here to up there to get this side of the parallelogram. So now we have the parallelogram completed. We need to draw a diagonal from the origin to this side over here and measure it. When we do that, we find that we get 9.9 centimeters. If we begin this ruler at 20 here and we end up at 29.9, so that line would be 9.9. We then multiply the 9.9 centimeter by the scale we were using, which is at 10,000 newtons per centimeter, and we get 99,000 newtons, or 99 kilonewtons, which is the same thing that we had previously when we calculated it. Now we will use a protractor to accurately measure the required angle. So we set our protractor here. We count from this 0 going that way. Let's see that a little closer, because this is 0, 10, 20, 30, exactly 40. So now we know that this C here is 40 degrees. And we know that our resultant is 99,000 newtons or 99 kilonewtons. And it is at an angle of 40 degrees from the larger force between the two original forces. Okay, so we completed this by scale drawing. This is our answer. So we looked at two examples, both by calculations using the cosine and sine rules, and that is not really required by CSEC for physics, but we also did them by scale drawing, and that is required for CSEC. Just to make sure that everybody understands, we will do a third example as you watch it being done in real time while I do it. Our question is 35 28.7 newtons and 28.0 newtons and an angle of 50 degrees between them. This is just a sketch. It doesn't have to be very accurate. We let that be the larger force, 35.7 newtons. We estimate an angle of 50 degrees somewhere here. Estimate. That's estimated to be 50 degrees. And this force here will be 28.0 newtons. So we have represented the two forces and the angle between them, as you see it there. So that that side is parallel to this side, and these two sides are parallel. We draw our diagonal here. This is our resultant in both direction and magnitude. We will call this A, and we will call this uppercase A. Well, since this is 50, this angle here will be 180 minus 50, which would actually be 130 degrees. We will call this side here B. That angle there will be B. This angle here that we want to find between the larger force and the resultant, we'll call that uppercase C. This side here will be lowercase c, and this, of course, here is 28.0 Newton. Okay, now that we have it set up like that, we will do the calculation. A squared is equal to B squared plus C squared minus 2BC cosine A. We move that square from this side and we get A is equal to the square root of everything there. So A is equal to the square root of B squared plus C squared minus 2BC cosine A. A is therefore equal to the square root, and this time we will start using brackets. We'll have a bracket here, another one here, meaning we will find the square root of everything in there. This piece we will do by itself, and then we'll minus that piece. So it looks like this. Now B, we said, is 35.7. So that would be 35.7 squared plus 28 squared. So 35.7 squared plus 28.0 squared minus 2 times 35.7 times 28.0 times the cosine of 130 degrees. Now we could do all of that in one step, so that A becomes square root of, open bracket twice, 35.7 squared plus 28.0 squared. We close that bracket there, minus, open bracket, 2 times 35.7, 35.7 times 28.0 times the cosine of 130 times the cosine of 130. We close this bracket here. Then we finally close that bracket there and we press equal. And we get 57.82 newtons. And since we are dealing with three significant figures, that would be 57.8 newtons. If you want to make sure, you could always say 57.8 plus or minus 0.05 Newton. Okay, so this is the magnitude of our resultant. Now we want to find this angle here. We know that A over sine A is equal to B over sine B, which is equal to C over sine C. Well, we are not dealing with angle B, so we'll cross that out, and we are left with A over sine A is equal to C over sine C. If you cross multiply, you get A times sine C is equal to C times sine A. And so you rearrange that formula so that you get sine C is equal to C sine A over A. Divide both sides here by A. You get this, which gives us C is equal to inverse sine, this stuff here, C sine A over A. Let's put in the numbers. Angle C is equal to inverse sine. Now we'll put in the numbers. We know that C is 28.0 times sine A, and we know that A is 130. All of that is to be divided by A, which we calculated to be 57.8, but we will use 57.82, close bracket. And we could do all of that in one step. If you are not sure about doing all of that in one step, you could do this part first, multiply it by that, write down the answer, and then divide by this. But we can do all of this in one step. So let's begin with, now this is sine. Inverse sine is that shift down there. So shift sine, inverse sine, open bracket, 28.0, 28.0 multiply by sine 130, sine 130 divide by 57.82, close bracket, equal to, and we get 21.7. So C is equal to 21.77, and we will approximate that to 22 degrees. So our answer is 57.8 newtons at 22 degrees. Now that is if we do it by calculation. And now we will do that by scale drawing. CXC does require you to know this. So 35.7 newtons and 28.0 newtons at an angle of 50 degrees between them. We have to choose a scale. If we say let 1 centimeter equal 10 newtons, then 35.7 newtons will be 3.57 centimeters, and 28.0 newtons will give us 2.80 centimeters. Now this will give us a drawing too small. So let's try to take that from 1 centimeter equal 10 newton to let 1 centimeter equal 5 newtons. Now in that case, 35.7 newtons would give us 35.7 divided by 5, 7.14 centimeter. And 28 newtons divided by 5, and that would give us 5.6, so 28.0 newton. At this scale, 5.6 centimeters. Now we can work with that. Of course, we could also try this one. Let 1 centimeter equal 4 newtons. In that case, 35.7 newton would give us 35.7 divided by 4, give us 8.925 centimeters, and 28.0 divided by 4 would give us exactly 28.0 newton, would become exactly 7.0 centimeters. Now we can choose this one here or this one. I prefer this one. So our drawing would be a little bigger than that, much bigger than that. So 8.9 centimeters. Start out here as 0. 1, 2, 3, 8.9 would bring us to this point. And we write in here 8.9 centimeters, which would represent 35.7 newtons. We accurately measure 50 degrees, 10, 20, 30, 40, 50. And from here through that point, we would draw 7 centimeters. So this force here is 28.0 newtons, which is represented by 7.0 centimeters. And this angle here is 50 degrees. Now we need to complete this parallelogram. This come up here, (8.9 centimeters), and then we come from this end, mark off that 7 centimeters. Where these two arcs meet, we draw a line from here to there. So we have a parallelogram. We draw a diagonal from here to there. And we measure that diagonal. We get 14.12, 14.2, 12, 13, 14.12 centimeters. So this diagonal here is 14.2 centimeters. Now, since our scale is 1 centimeter is equal to 4 newtons, then 14.2 centimeter multiplied by 4, and that would give us 56.8 newtons. That will be the magnitude of the resultant. And since we wanted to find this angle here, we will just measure it. 10, 20, 21, 22, somewhere between 22 and 23, we could call it 22, we could call it 23. So as we can see, our resultant from the drawing is, the magnitude is 56.8 newtons at 22 degrees. Let's compare that with what we got from calculation. This is the calculation. We got 57.8, and by scale drawing we have 56.8. By calculation we got the angle was 22 degrees, and by drawing here we got the angle here is 22 degrees. Now normally we would see this formula like this: a squared is equal to b squared plus c squared minus 2bc cosine a. But you may also see it like this: b squared is equal to a squared plus c squared minus 2ac cosine b, or c squared is equal to a squared plus b squared minus 2ab cosine c. Notice that if you begin with a lowercase a here, you end up with an uppercase A here, and the rest of the stuff would be the other two sides. Same thing here. You begin with a side B, end up with an angle B here. Begin with a side C, end up with an angle C over here. And the other stuff there would be the other two sides. Begin with the P here. You end up with an angle P here. and if the other two sides are Q and R, and so on. And the same thing applies for the sine rule. We know A over sine A is equal to B over sine B, which is equal to C over sine C. You could as well say P over sine P is equal to Q over sine Q, which is equal to R over sine R, or D over sine D is equal to F over sine F, which is equal to K over sine K. It all depends on how the angles on the sides are labeled. So we have reached this far, but we are not yet finished with section A. A little more to go, as we need to deal with calculations this time, involving two forces that are exactly at right angles to each other. CSEC requires that you know this, not just the scale drawing, as we did previously, with the angles that are not 90 degrees, but with the angles that are 90 degrees, we have to know how to do those calculations.